Hi, my name is Bailey Chambliss, and this is my Physics 2211 lab number 4, Oscillations. So the purpose of this lab was to examine the oscillating motion of a mass attached to a spring, as well as to predict this motion using the fundamental principles. So in analysis, using the Python and tracker models, the predicted motion of the mass is compared with the actual mass of the object. Energy changes that occur in the system are also plotted. And then a preview of results. The observed and actual models share similar x and y axes, and the total change in energy is equal to 0. So the key concepts of this lab, the net force of an object is represented in the code as F net equals delta P over delta T. The velocity update formula is shown as the final velocity is equal to the initial velocity plus sum of net forces divided by mass times the change in time. Position update formula is shown as the final position is equal to the initial position plus the average velocity times the change in time. Our energies, K equals 1/2 mv squared. Our gravitational potential energy is mg delta y, and then our spring potential energy is 1/2 ks squared. So for our energy principle, that is described as the change in the energy of the system, or delta E, is equal to the work done on the system, so W surroundings, plus the exchange of thermal energy between the system and the surroundings, which is Q. So delta E system equals work surroundings plus Q. So delta E system is equal to delta K, so our change in kinetic energy, plus delta UG, change in gravitational potential energy, plus delta US, which is our change in spring potential energy. So delta ES equals 1/2 mvf squared minus vi squared plus mg delta y plus 1/2 k sf squared minus si squared. So our change, the change in energy of the system will sum up to 0. So this is our tracker model.
Good night. Of course. I actually have a softer blanket if you want it. Yeah, let me finish recording this and then I'll...
So the results of our tracker model are plotted here. So for this, our system is the Earth, the spring, and the mass, which in this case we consider to be everything. So that means that there are no surroundings. And so because the system is set to everything and there are no surroundings, work done by the surroundings on the system is equal to 0 and Q equals 0. So our object's mass was 0.402 kilograms, our video speed was 0.095 frames per second, our start time was 0 seconds, end time was 9.972 seconds, our initial position was negative 0.12, negative 0.670 meters, and our initial velocity was 0 meters per second. So in this, you can see our Python code conditions. We translated those initial conditions from the tracker model into Python. So our mass is the same, initial position is the same, and velocity is the same. But the Python code is just going to model it under ideal conditions. So this is our computational loop. So a little discussion of our results. So for the change in energy versus time graph, which is the top right graph, we can see that as the change in spring potential energy increases, the change in gravitational potential energy decreases accordingly. This is shown via both lines crossing the x-axis at the same time. So for our position versus time graphs, which are our bottom two graphs, while both graphs show strong resemblance, the predicted data in the x direction is slightly more accurate. And then some sources of potential error are the absence of other energies, friction unaccounted for, poorly placed data points, and human error. And finally, our discussion questions. Is the energy principle satisfied? So according to the graph created with Python code, the energy principle is satisfied. This conclusion can be drawn because at any point in the graph, the total summed energy would amount to 0. The oscillation between change in gravitational energy and the change in spring potential energy is the best representation of this, as they have an inverse relationship. So for our estimation of oscillation periods, our average oscillation period in the x direction is 1.519 seconds, Our average oscillation period in the y direction is 1.633 seconds. Our difference is 0.303 seconds. The difference between oscillations has an impact on spring force, spring potential energy, and the calculation of the spring constant. The difference could be caused by any of the examples of human error or unaccounted for forces. Thank you.